In the last class, we introduced this Armijo search, okay? So we just review a little bit about this. And so if L is not smooth, and how do we determine the step size? And without the capital L, okay? So one of the choice is the Armijo search. So we need to determine two things. First, we determine how to compute it, and then we determine when we should stop. Okay, so this is from the constant step size. Okay, so we didn't talk more about that. Okay, so this is what we talk about the Armijo search. Okay, this is the univariate function to measure the increment of the function value. Okay, we can see here if you choose 0, step size equals 0, your function value will not change. And okay, so if you increase a little bit, your function value will decrease. Okay, will decrease until here you get the minimum of the function value. And then if you go along this direction, your function value will increase. Okay. So what we want the step size, okay, below these lines with the slope equals to negative sigma, the norm of gradient of fx squares, okay. We want the step size below this line. So we get this inequality, okay, this phi alpha is less than this line with this slope, okay. By the definition, we have this, we substitute phi alpha with the definition of phi alpha, then we get this. This is what we call the sufficient descent condition or Armijo condition. Okay, so with sigma belongs to 0 and 1. Another thing is we need to find a way to compute a value which satisfies this Armijo condition, okay? And the question is, if we choose any alpha satisfies the Armijo condition, can we get the convergence result? Unfortunately not, okay, because the Armijo search accept very small step size, okay? So we use this backtracking, okay? We began from an initial alpha, okay? If it not satisfy this inequality, then we times a beta, which is called backtracking parameter, which is belongs 0 and 1, okay? So this combining backtracking and the Armijo condition, we call it Armijo line search. And with this Armijo line search, the gradient descent or the descent algorithms can have somehow convergence in the sense of the norm of the gradient. Okay, so this is algorithm gradient descent with Armijo line search. Okay, we choose negative gradient as a descent direction, and then we use backtracking until the Armijo condition is satisfied. Then we go to the next point. Okay. About the convergence, we will not discuss anymore. Okay, so we can have the convergence of sequence with convexity. Okay. So if you assume your function is convex, you can have the convergence of your iteration. Here we introduce some other line search or other conditions. Okay, the sufficient descent condition actually is not enough by itself to ensure the convergence, as we mentioned before, because it accepts very short steps. Okay, so to guarantee the convergence, we add another condition which is called the curvature condition, okay, to improve or to overcome the bad points of the sufficient descent. Well, how does it work? This picture explains how does it works. Actually, we want the accept step size, okay? For example, this interval is acceptable step size, and we want the slopes at each point is not bigger than this one, okay? It's not bigger than this one. It's smaller than the slope of this. So you say, for example, if you some point at here, which has a bigger slope, okay? Which has a bigger slope, but it means you have an even smaller step size. So this curvature condition means we accept some because this is negative, okay, this is negative and this is also negative, so we accept only slopes which is smaller than the initial slope. Okay, we can go this picture. So to get combining sufficient descent and the curvature conditions, these two conditions together, we call it the Wolff conditions. Okay, the first is what we introduced before, the Amigal condition or sufficient descent condition. The second one is the curvature condition. So the Amigal condition accept the step size which below this line, okay, this line. So they accept this part of the curvature and also this part of the curvature, okay? And together with the curvature condition, we accept the part which has a slope smaller than this desired slope, okay? So it exclude the initial these steps, okay? I'm sorry. It accept bigger slopes. For example, here the initial slope is very small, okay? So we accept bigger slopes. So for example, here we accept here, and the slopes from this point to the right side is bigger than this desired slope. But on the left side it's smaller. So with the curvature condition, we will not accept the initial step size, the initial part of this phi alpha, okay, which means we didn't accept the very small step size anymore. So these Wolff conditions usually can guarantee the convergence, okay. So this is what we talked about last class. And then we go to another kind of step size rule, which is called diminishing step size, okay? We recall a little bit. The problem is we want to minimize f, okay, without any constraints, and we choose the gradient method, okay? So we can use like a constant step size, okay? We can use constant step size which choose alpha equals to any number between 0 and 1 over L. Actually, we usually can choose 1 over L, which is a very safe step size and efficient. Of course, if the function is not ellipsis continuous, we can use Amigal search, okay? Backtracking plus the sufficient descent condition. But there is some problems, okay? First, if L is L smooth, okay, but without knowing but we do not know the value of capital L. So in this case, we cannot use the constant step size as for example 1 over L. It doesn't make any sense. Of course, you can have some estimations, some other strategies, but generally speaking, we cannot use the constant step size. Of course, another problem is if the evaluation of the function value is very expensive. For example, in some applications, when you want to calculate fxk, sometimes you need to make simulations, or your problem is has a very large scale. The computation of function value is very expensive. So if you do a lot of backtracking, if you do a lot of times of backtracking each iteration, it would be very expensive. So in this case, we propose this kind of diminishing step size. Okay, so this is a theorem about this kind of step size and its convergence. So we suppose xk is a sequence generated by this gradient method, okay? We assume f is L smooth on the whole space, and there are two positive constant C1 and C2. For all k, we have these two conditions hold. First actually is to say it's a descent method, okay? If you times minus on both sides of this inequality, it tells you that the decay is a descent direction, and even it's something like a sufficient descent direction. And the second inequality, the norm of decay square is less than C2 times the norm of the gradient square, which means the decay is bounded, okay? So with these two inequalities, we know decay is the descent direction, decay is bounded. So we suppose this is diminishing step size rule, okay? First, alpha approaches 0, okay? It could be very small when k is large enough. And LK is not summable, okay? It's not summable. Actually, this means the step size can approach 0, but not so fast, okay? Not so fast. So the result is the function value either approaches the minus infinity, or the function value converts to a finite value, okay? And the gradient converts to 0. Furthermore, we conclude that every limit point of xk is a stationary point, okay? Is a stationary point if it has a limit point. Okay, next we go to the proof and see how does this kind of diminishing step size works. First, because you have the L-smooth assumption here, okay? Of course, we can use descent lemma to measure the increment of the function value. Okay, so you have fxk is less than fxk, the first term and the second term, which the decreasement of the function value can be bounded by the first term and the second term, okay? And then we use assumptions here, okay? You have two assumptions. First is about the inner product of the decay and the negative gradient. And the second one is the norm of decay. So first we use the decay is a descent direction, okay? Somehow sufficient direction here. We get this one, okay? So, and then we combine these two terms together. We get the function value fxk is less than fxk plus 1, less than fxk minus this term. And don't forget, and then we use the assumption about the step size. Let's go back. We have two property of the diminishing step size. First, alpha k goes to 0, and then it is not summable, okay? First, we use this approaches 0. Alpha k approaches 0. We concentrate on this coefficient of the second term, okay? We see here, there are two terms. One is a first order term, and the second is, and another one is the second order term of alpha k. Since alpha k approaches 0, then we know the first order can denominate these terms, okay, this coefficient. So this is explanation. So we know alpha k approaches 0, so the linear term dominates the quadratic term, okay? So we can find some positive constant c, which is c, okay? Such that for large enough k, this coefficient can be written in one constant c, okay? Actually, since the first term dominates, we can somehow only use the first term here, okay? We can delete the second term with even bigger constant. Okay, so this means for large enough k, your function value is decreasing or monotonically decreasing, okay? But remember, for large enough, for all the k is greater than k bar. So we know for k greater than k bar, the function value either approaches, here it's the negative infinity, or the function value converts to a finite value, okay? How do we get this result? Let's review a little bit. First, we use descent lemma because of the L-smooth assumption, okay? So we use descent lemma to measure the discrement of the function value. And then we use here, we use the alpha approaches 0, and we get a new upper bound, which is just related to alpha and a constant c. Sorry, here you have the square here. You have a square in this inequality. Okay, and next, since we have this inequality, okay, we began from this inequality. We suppose f converges to a finite value, okay? We adding the above inequality. Which equality? We adding this inequality. Overall, k is greater than k bar, okay? So we adding the above relation, which is the inequality, and for all k greater than k bar, and we have this inequality. Okay, we have this inequality, and also we assume the f converges to a finite value. So this series is converge. Okay, this series converge. And another, here we use another property of the diminishing step size. What is diminishing step size? Which says alpha approaches 0, we have already used, and another is it's not summable, okay, non-summable. We use a non-summable here. Since alpha k is non-summable and this is positive, so we cannot find any epsilon greater than 0 such that for all k is greater than k bar, the gradient is always strictly greater than epsilon k. This means the limp inf of the norm of gradient is equal 0 as k approaches infinity. Okay, this comes from the property of alpha is non-summable. Okay, sorry. Okay, so now up to now we got the limp inf of gradient of the norm approaches 0. Okay. To show the gradient approaches 0, we assume in another direction. Okay, we assume that the lim sup of the gradient is greater than epsilon. Okay, which epsilon is a positive number. Okay, from the limit sup is greater or equals to epsilon, and the limit inf equals 0, then we can get two subsequences, okay? To subsequence such that the mg is less than ng and is less than mg1. For k belongs to mg1 and ng, the gradient is greater than epsilon over 3. And for another part, for k is greater than or equals to ng or less than mg plus 1. The gradient, the norm of the gradient is less than epsilon over 3. Actually, one is from the limit sup is greater than 0, and another is from limit inf equals 0. Okay, so we have these two inequalities for different k. Okay, for different for k belongs to different interval. Then we already know that this series converge. Okay, this series converge. So for the tail, for a convergent series, the tail can be small enough. Okay, can be sufficiently small. So for any g bar, okay, because we are considering the subsequence, so we're considering a g bar which is sufficiently large so that the tail of this convergent series could be small than this upper bound. Actually, it could be as small as you want, but so we want this upper bound. In the next slide, you will understand why we want this upper bound. Okay, just keep in mind. Okay. So for any g for any g, the index of the subsequence is greater than g bar, and for m belongs to mg and ng minus 1. We have this, okay? So first we use the I forgot the name of the inequality, okay? And first we use the inequality here, we get this one. And then we use the definition of the L smooth, okay? So we use the, there is a gradient here. This should be the gradient of f, xk plus 1 minus the gradient of f, which is less than this. We use the definition of the L smooth, which means the gradient is ellipsis continuous. Okay, so we get this one. Here we just use the xk equals to L, just use the scheme of the gradient descent, okay? And here we from this this inequality, okay? The only difference is we use the inequality about the decay. Did you remember we have two property of decay? First is decay is a sufficient descent, is the descent. Okay, the inner product of the first is this is first inequality about decay. The second one is decay square is less than C2, the gradient of okay. So you have two inequality. First means it's descent, okay, and second means it's bounded. So we use the bounded of decay in this inequality, so we get this one. So that's why you have L square root of C2 and this series and this summation. And then from this one actually because the m belongs to mg and ng minus 1. We go back to the last slide, okay? So we divided the subsequence into two parts. If k belongs to mg and ng, okay, so the gradient is greater than epsilon over 3. If k is between ng and mg plus 1, it is bounded by the epsilon over 3, okay? So here, the m is between mg and ng minus 1. Of course, it's also between mg and ng. So we know that the gradient has a lower bound, okay? So we use the lower bound here, okay? We use the lower bound of the gradient here. So that's why you have the square here, and you have the epsilon here, okay? And then we use, because here the G is greater than the G bar. In the last slide, we already say that for any G bar, for any sufficiently enough G bar, we have this series is bounded by this term, okay? So we use this term here. So we get this 3L square root of C2 over epsilon times this term. So you have this epsilon over 3. Okay, so remember this inequality. The norm of gradient of xng minus the gradient of xf at xm is less than epsilon over 3. So we use the last inequality. We can have the norm of gradient of fxm is less than the gradient of fxng plus epsilon over 3. This is exactly what we get in the last slide, okay? And for any g greater than g and any m between m and ng minus 1, we also know that let's go back. If some index between mg, okay, and between mg and ng, so it has an upper bound, okay? If the n index is greater than ng and less than mg plus 1, which has an upper bound, okay? So for any g is greater than g bar, we have this inequality from the last one, okay? And we also have this, the norm has an upper bound, also epsilon over 3. So that's why you have 2 epsilon over 3. Okay, together, sorry. This has some problems here. If you want to get 2 epsilon over 3, okay, this is for all m is greater than mg, okay. You get this inequality, the first inequality, for any m between mg and ng minus 1. And for any m which is greater than ng but less than mg plus mg plus 1, you get this norm has an upper bound also equals to epsilon over 3. So together you have this the upper bound of the norm of the gradient is 2 epsilon over 3 for all m is greater than mg, okay? This means for any m, for any index which is greater than which is large enough, the gradient has an upper bound, okay, which has a upper bound. But this has contract with the assumption that your limit sup is greater than epsilon, okay? It's greater than epsilon for large enough k. So this gives our result, the result that the norm of the gradient equals 0, approaches 0. Okay, finally, if x bar is a limit point of xk, then we say the function value converges to a finite value, okay, because it's continuous. And then we have the gradient of xk approaches 0, which implies the gradient of x bar is equals 0 because of the continuity. Okay, actually this is the application of the diminishing step size, okay? You can use a gradient method with the diminishing step size and then you can have this kind of convergence result. Another application of the diminishing step size is the subgradient method, okay? I will introduce this briefly. It's a subgradient method. If we consider still this unconstrained minimization problem, but f is convex but not differentiable, okay? Since it is not differentiable, it's difficult to define or to check whether a method is, whether a direction is the descent or not descent. So usually the subgradient, because in the differentiable case you use a gradient, okay, but here it's not differentiable, so we use a subgradient, okay? The subgradient is a descent, usually is may not be a descent direction. The subgradient method works like this. So you have xk and you have the step size, you have the minus subgradient, okay? This gk belongs to subdifferential of f at xk. And the step size we use square summable but non-summable. Actually, it's a special case of diminution, okay? Since it's square summable, alpha k approaches 0, okay, as k approaches infinity. And it's not summable, okay, it's non-summable. But this square summable means the alpha k approaches 0. And for the convergence, we usually assume x is a minimizer. It's not strong because it's a convex, so you always have a minimizer. And the gk is, no, it's not always, it's not a strong assumption. And usually we assume that the GK is bounded for all K. Actually, if your sequence is bounded, this can always be held, okay? And we also assume that the initial point, the distance between the initial point and your solution is upper bounded by some constant capital R. Okay, so first, the conclusion is that if F is convex and above assumptions are satisfied, then you have your F best K approaches your optimal value, optimal function value, as K approaches infinity, where F best K is the minimum among all the function values for all the iterations up to now. Okay, let's review a little bit the definition of the subgradient. Okay, if you have a convex function, we say a vector D is a subgradient of fx point x. If this satisfied, okay, if this satisfied for all z belongs to the Rn. Okay, for all z, sorry, there is something missed here. For all z belongs to Rn. So remember, keep this inequality in your mind because this is what we used in the analysis of the convergence of this theorem. Okay, so we assume that x star is a point that minimizes f. Okay, so we have this. Actually, the first is just expansion of these square terms. Okay, you use the definition of the subgradient method, and then you get this one, and then you expand this square terms. You have this one. Okay, so this GK is a subgradient. Okay, you use the definition of the subgradient here. Then you can have alpha k times the distance of the function value. Okay, the distance of the function value. Okay, so you have this inequality here. Okay, you apply this inequality from I equals to 1 to k. Okay, so you have this inequality. You have two summation terms here. Okay, and then we're using two facts. The first, this square term is non-negative, and then we also assume that this assumption holds. Okay, so we can have the summation of these function value terms related to the function value terms is less than r squared, which are corresponding to this term, and also you have these terms here. Okay, you have these terms here because you delete this term. Okay, because you eliminate this term because this is non-negative. This is non-negative. Okay, so you have this term here. Left side is a summation of the function value, and right side are some constant plus a summation. But remember, this GK is also bounded. So we are combining the last inequality with this one. So we analyze this inequality first. Okay. So this is a summation about the function value. This is greater than we take the minimization of fxi from I to k. Okay. And here we substitute this minimization by f best k by the definition of f best k. Okay, so we combine this inequality with the inequality we get this one. This inequality is about the upper bound of the summation of the related to the function value. Okay, we combine this inequality and this inequality together, so we get f best minus f star is equals to, this is by the definition, is bounded by this upper bound. Okay, we analyze this upper bound. Okay, you have constant here. Okay, and you have a summation of the steps here. Okay, and you have a summation of the square of step size times the norm of the subgradient. Okay, remember the summations. First, this GI is bounded. Okay, so we can use the summation of the GI is bounded, that we update the upper bound. Okay, we update the upper bound. So you only have two summations here. Summation is a summation of alpha and the summation of alpha square. Remember what kind of step size we use. We use a diminishing step size, but exactly it's a non-summable but square summable. Okay, so square summable, this series converge. Okay, this is a finite value. And non-summable, this means this summation will approach infinity. So it means this upper bound will approach infinity as k approaches infinity. So this means the fk best will approach fx star, f star. Okay, so we recall the step size is square summable, but non-summable. So we get f best approaches f star. Okay. So we make some numerical experiments or some comparisons about these three different kind of step size, which they are constant step size. Okay, we use 1 over L, but we want to minimize our quadratic function. Okay, and we assume that Q is a symmetric positive definite matrix. Okay, and then the Lipschitz constant is just the maximum of the eigenvalue of this Q of this matrix. Okay. Of course, we generate a positive matrix, so in your program you can control the maximum value of the maximum eigenvalue of the Q. Okay, for the constant set size we choose 1 over L. Actually, you can choose a value which is closer to 2 over L, but not 2 over L. But actually, for stable or safe step size, we choose 1 over L. Okay. For Armidjo search, we choose the sigma. The sigma should be between 0 and 1. Okay. We choose 10 to the minus 4. 10 to the minus 4. And beta is the radius related to the backtracking. Okay. If the Armidjo condition didn't succeed, is not satisfied, you need to do a backtracking. So beta k is a backtracking parameter. And alpha k is the initial step size. Okay, we choose 1. And another is a diminishing step size here, which we want a summable, square summable, but non-summable. Okay, we choose some a0 over k plus 1. Actually, we choose a0 here equal to 1. Actually, you can choose something even bigger or even smaller. It doesn't matter. Okay, so we can have, this is a graph about the function value. Okay. So we can say the gradient or the method with the diminishing step size. You say the function value will increase, okay, but later, remember, if the k is large enough, your method, the result in the diminishing step size is that it's not a descent method, but when the index of the iteration is large enough, it becomes a descent method. Okay, so when the k iteration somehow is large enough, here it looks like when the iteration is greater than 50, it becomes a decreasing. Okay, the function value begins decreasing, and we see the blue part is the fixed step size. Okay, it's decrease, but obviously here Armidjo search is better than the Armidjo search here is better, okay? Is better. And here is the norm of the gradient, okay? So here is the norm of the gradient. You also see that the diminishing, for the diminishing step size, the norm of the gradient increase and later it decrease. But finally, both of these three kind of step size, the method with this three different step size will converge, okay? Will converge. Okay, so this is about the diminishing step size about today. We use two kind of reference. You can find the first theorem about the diminishing step size in the Boteseca's book, Nonlinear Programming, and then you can use the subgradient. You can find the details about the subgradient method, the convergence analysis, the step size in this survey paper from the Stanford University. Okay, this is all about the class. In the next class, we will go to another algorithm, which is the Newton method, which actually has a weaker convergence result, but has a even faster convergence rate.